Baryons are constructed through simple addition. You sum the mass of three quarks together. Mesons require an entirely different architecture. Moving to a two-quark system, a quark and an antiquark, means calculating a physical structure based on opposition. We're taking the ODTBT geometric classification framework, which successfully mapped baryon structures, and applying it to 6 Pseudoscalar mesons. The objective is to derive their exact mass ratios using geometry without relying on any free parameters. Because a meson is built from a quark and an antiquark, its internal dynamics rely on a subtractive electromagnetic cancellation model. The constituent fields cancel rather than sum. This creates an immediate stress test for the framework. The particle group contains neutral mesons defined by complete subtractive cancellation and charged mesons that retain a net electromagnetic charge. Both exist and both must be accounted for geometrically. If the classification model is physically accurate, these distinct electromagnetic charge states will naturally segregate, mapping to predictably different topological pathways. The primary geometric target for these mass derivations is a metric called zero-dimensional vertex, or ZDV, proximity. This value dictates how closely a particle's internal structure aligns with the physical vertex of an icosahedron. The operational standard for this test is strict. The framework must evaluate the flavor algebra of the particle and blindly predict its CDV position before a single calculation is run. The final scan of the meson secto yielded definitive results. Out of the 6 particles tested, 4 achieved fully validated mass matches. 2 remained unresolved. Those 2 unresolved cases are not random mathematical errors. They both isolate highly specific anomalies regarding how this strange quark couples within this geometry. Mapping the exact parameters where the framework breaks down defines the true boundaries of quark coupling. Evaluating these geometric failures is how we locate the next layer of the physics. Consider the eta octet and eta prime singlet. Both neutral mesons contain similar quarks but have wildly divergent masses. Eta mixes quarks subtractively, forcing it to an icosahedral vertex. Eta prime mixes additively, pushing it outward into edge territory. Before calculations, a formal prediction was recorded. The subtractive eta maps to a vertex, and the additive eta prime maps to an edge. Phase 1 scan results confirmed the geometric divergence. The eta secured a ZDV proximity of 0.9969, placing it at the vertex. The eta prime registered at 0.467, leaving a 0.53 delta separation. This geometric separation mirrors the structural mass split traditionally governed by the QCD U1 axial anomaly. The framework correctly predicted the physical structure. Plotting the computational results for all 6 mesons reveals clear structural patterns. The eta meson achieved a flawless match, driven directly from F6 geometry. Isolating the charged mesons, the charged kaon and pion, a strict selection pattern emerges. The charged particles uniformly selected the dual recursion Spinor channel to achieve their validated mass matches. By contrast, every tested neutral meson natively bypassed the Spinor pathway, exclusively selecting the single recursion scalar channel. The data presents a clear hypothesis. A net electromagnetic charge forces a particle into a Spinor pathway, while perfect electromagnetic cancellation allows stabilization in a scalar pathway. The geometric framework works cleanly and predictably until it encounters specific quark flavor combinations that the underlying geometry forcefully rejects and shatters. Take the charged strange kaon, or K+. When processed through the Spinor channel, it achieves a highly validated match with a 0.077% error rate. Now compare that to the K0 neutral kaon. It contains the exact same strange quark content, but because it is electrically neutral, it processes through the scalar channel. This chart shows the breakdown. The charged K+ validates perfectly, but the neutral K0 suffers a massive foundational error. Identical strange quark mass performs 133 times worse in a scalar architecture. Even using the successful eta meson seed configuration, K0 performs 100 times worse. Strange quark coupling depends entirely on the channel. Spinor architectures seamlessly accommodate strangeness, but scalar architectures do not. Neutral strangeness requires an entirely new theoretical treatment. A paradox exists in the computational data. The optimization algorithm produced mathematically exact level 2 mass matches for both the failed K0 and the eta prime. These matches are continuous optimizer artifacts. An exact numerical result does not automatically equal valid physics. If an algorithm has infinite degrees of freedom, it can bend the numbers to fit the target, completely masking a broken geometric foundation underneath. This graph plots level 1 errors against a strict 5% threshold. The 4 validated particles sit safely below this line, securing their credibility. The open cases blast past that threshold, meaning their exact level 2 matches were actively rejected to maintain integrity. Methodological discipline means rejecting perfect math when it lacks physical geometry. A valid framework must remain a tool for discovery, not an exercise in curve fitting. The Meson sector stand concludes with 4 validated mass matches and 2 explicitly documented open cases. A transparent 67% validation rate with clearly defined boundaries is scientifically superior to a model that forces a 100% success rate through mathematical tricks. The failures of K0 and eta prime act as precise cartographic markers. They show exactly where the geometric model hits the limits of known quark behavior. They isolate the undeniable friction between scalar topologies and neutral strangeness. A theoretical framework that produces only confirmatory results is likely overfitted. Structural failures are the signature of a model making genuine contact with reality. The next phase for the framework will be applying these rules to the much heavier charm and bottom meson sectors. We have to determine if this strict charge segregation, Spinor channels for charged particles, scalar for neutral, holds true at massive energy scales. Resolving the K0 and K+ anomaly will ultimately require defining a new mathematical correction term, designed specifically for scalar strangeness. This parameter-free geometric modeling has successfully predicted structural behaviors that historically required complex gauge theory to explain. Theoretical progress requires mapping the geometries that refuse to fit. These anomalies are the structural coordinates for the next